Hello everyone, myself Dr. Rekha, professor in SJBIT. Today we will study regarding with Introduction to Basic Electronics Module 2. So in this Module 2 we are going to cover oscillators, different types of oscillators. So sustained oscillation, condition for that, and also the a ladder network oscillator, Wien bridge oscillator, multi-vibration, single phase astable oscillator, crystal oscillator. So first of all, you have to know what is an oscillator. An oscillator is a circuit which basically acts as a generator. So generating the output signal which oscillates with constant amplitude and constant frequency. So we know that an oscillator is an electronic circuit which converts an DC signal to AC signal without having any external input signal to start. So we can say that is also a converter. So oscillator produces a continuous, a repeated alternating waveform without any input signal, used in genetic clock signal, frequency of audio and video signals. So we know that in oscillators it has got two blocks which is known as amplifier block. So amplifier block, which will be a gain of an amplifier, is represented by an E. So gain is known as output voltage divided by input voltage. So gain of a feedback will be represented as beta. So here also beta will be equal to output divided by input. So in particularly in oscillator, we will use a positive feedback. So first of all, we have to know what is a feedback circuit. So part of the output is fed back to the input is known as a feedback. So there are two types of feedback, which is known as positive feedback and negative feedback. So in positive feedback, that is, we will know that it will be used in the oscillator, and a negative feedback will be used in the an amplifier. So when the output is fed back in such a way as a, that is, output is in phase with the input, then we will call that as a positive feedback. If output is out of phase with the input, we will say that is negative feedback. So that is in positive feedback and oscillators will be used. So block diagram of an amplifier stage with a positive feedback is shown in the figure. So that is that the amplifier provides a phase shift of 180 degree, and the network feedback network, which has to be designed to produces a further 180 degree phase shift of a 180 degree. So in this, the feedback amplifier, so we are going to derive this for an equation which will be knowing that with an A beta must be equal to 1. So to produce a sustained oscillation, we know that to get a 180 degree phase shift, so there are two conditions which has to be satisfied here. That is, we know that an oscillation. So there are two types of oscillation, which is known as that is damped oscillation and undamped oscillation. So damped oscillation means whose amplitude goes on reduces with the frequency constant. So we will say that is damped oscillation. So undamped oscillation means those frequency won't amplitude won't go reduces. This is mainly due to the I square R loss. So we have to, for the gain of an amplifier, we have to derive that as in EV by 1 minus of A beta. So in this, we have to know two different criteria, that is, which is known as A Barkhausen's criteria, which is an total phase shift around a loop as a signal process from the input through an amplifier feedback network back to the input gain complete a loop is as to produces a phase shift of 0 degree or 180 degree. Of course, an integral multiples of 2 pi radians. The magnitude of an produces open loop gain of an amplifier and a feedback gain, closed loop gain, that is magnitude of A beta must be equal to 1. So if it is the two condition is satisfied, then only you will get a sustained undamped oscillation. So sustained undamped oscillation means we won't get any losses, that is amplitude won't reduces with respect to the frequency. So we have to take care such a way that the amplitude or an I square or losses should not go fall, so that you won't get a sustained oscillation. So if the Barkhausen's criteria is satisfied, then only you will get an oscillator. Since an oscillator has no input, so that is the output is fed back to the input. So you can see here A beta is less than 1, we will get a damped oscillation. If A beta is greater than 1, we will get an undamped oscillation. And A beta is greater than 1 is called as overdamped oscillation, and A beta is equal to 1, we will get an undamped oscillation. So you can see the figure that how the signal wave is seen here, that is undamped oscillation as well as overdamped oscillation. You can see here in figure that is a damped oscillation, that is an A beta will be less than 1. So overdamped oscillation, that is which will be amplitude goes on increases. So in case of A beta is equal to 1, so the amplitude will remain same for a particular frequency. So since it is an oscillator circuit, so since it is acts as a generator, so it has to generate undamped oscillations. So if you come to a classification of oscillator, so you will get an 8 to 10 marks here. Write the classification of an oscillator. So direct question they will ask. So at that time you have to ready to write the classification of an oscillator. So we know that how the oscillators are classified is mainly broadly divided into following two groups. Sinusoidal oscillator, which provides an output having a sine wave, or we will call this as an harmonic oscillators. And then it is divided into non-sinusoidal or relaxation oscillator that produces an output which has a square wave, rectangular and sawtooth waveform operators of the pulse. So you have seen in the signal generator that is different waveform generation. So what are the different waveform generation? That is sine wave, one square wave, triangular wave or sawtooth wave. Even pulse shaping, that is pulse, can be produced. So the here in oscillator, that is in signal generator, we were going to use then an oscillatory circuit. Then we will study what is this a sinusoidal oscillator and also an relaxation oscillator. And also it is classified according to the feedback circuit what we are using, that is sinusoidal oscillators is further classified into a low frequency or audio frequency oscillator and high frequency, that is radio frequency oscillator, and also it is classified as a mega frequency which is known as an LC oscillator. So LC oscillators is further classified into, and that is according to the tank circuit, which will be known as Hartley oscillator as well as Corbett oscillator. So for your syllabus only the and low frequency oscillator generator is there. So low frequency oscillator is known as audio frequency oscillator. So what is the range of an audio frequency oscillator? So audio frequency is nothing but a few hertz to 20 kilohertz, which will be producers will known as a audio frequency or low frequency oscillation. So low frequency oscillators are further classified into two types, which is known as RC phase shift oscillator or a ladder network oscillators. So RC phase shift oscillator or a ladder type network oscillator and also a Wien bridge oscillator. So in this you are going to study that is two different types of oscillators, a ladder network oscillator which is known as RC phase shift oscillator and also a Wien bridge oscillator. So they will give direct question on this. Say write a neat circuit diagram of a ladder type oscillator and briefly explain. So at that time you have to write the circuit diagram, brief procedure, brief an explanation on this, and you have to write the equations. So here waveform is there not there, since it is generating only a sinusoidal waveform, so the waveform is not required. So if you come to the ladder type oscillator, so the name itself says that it is the circuit will be in the form of ladder. So we know that an oscillator consists of an amplifier. So you can see here that is an circuit, you can see that is we can amplifier, the BJT is used as an amplifier, and also an feedback circuit consists of an RC ladder type network. So you can see a 3-section R1, C1, R2, C2, R3, C3 and R which will be used so that and it is designed such a way that each section will produces an 60 degree. So 60 into 3, so you will get an 180 degree. So that is what is Barkhausen's criteria. The Barkhausen's criteria is nothing but it has to produces 0 degree, entire phase shift should be a 0 degree or 360 degree. So here it is designed such a way that an transistor will produces 180 degree phase shift and a tank circuit will be produced, a feedback circuit will produces another 180 degree phase shift, so which produces a sustained undamped oscillation. So in this, a simple RC phase shift oscillator based on a 3 stages CR ladder network is as shown in the figure. So and also R1 and R2 you can see here, which acts as a biasing of a transistor, and R3 will act as an biasing of the emitter of the transistor, and capacitor which is connected as a bypass capacitor in order to bypass the give the stable to the transistor. So in order to produce a transistor as an amplifier, it has to act in an active region, that is, so that Q point should be selected in an active region so that it will produce as an amplifier and 180 degree phase shift. So in this, the total phase shift provided by CR ladder network connected between collector to the base is 180 degree at the frequency of oscillation. The transistor provides the other 180 degree phase shift in the order of an overall phase shift will be 360 degree and 0 degree. The frequency of oscillations for the circuit shown in the figure F will be equal to 1 over 2 pi into root 6 into RC. And a simple problem they will ask for the 4 to 5 marks in the examination. So determine the frequency of oscillation of a 3-stage ladder network oscillator in which C is equal to 10 nanofarad and R is equal to 10 kilo ohm. So F is equal to 1 over 2 pi into root 6 into RC is the RC ladder network frequency. So we know that they have given in the first collect the data and read the problem and collect the data. So C is given and R is given. So substitute that values in the frequency F is equal to 1 over 2 pi into root 6 into RC. So root 6, that is roots will be only to the 6. So don't take that root to the R and C values. So the F will be is equal to 647 Hertz. So you have to calculate individually so that you won't go wrong in your examination. And meanwhile, so one more you will come to known as a Wien bridge oscillators. So in this Wien bridge oscillator, so we'll come to know that is